you to my lecture today. Give me 1 second. Yeah, can you all hear me, right? Okay. I want to welcome you once again to my lecture today. Today we have very important topic that we call probabilistic graphical model. Of course, the difference between 3021 honor and the conventional 2021 is just that we're actually going to go a little bit harder. But I want to tell you everything is basically going to be easy. All what I need from you is to sit back, listen and ask question, if actually you need your clarification. Okay, so I want to introduce you to probabilistic graphical model in the outline. That's what I have. You've been introduced to that. And of course, I'm going to walk you through applications. But before we get started, I want to first, get you familiar with some basic terminologies. Now, let me tell you the idea behind probabilistic graphical model. We actually want to have a way to represent complex situations, complex variables. How can we actually represent complex variables using the idea of graph and probability? In probabilistic graphical model, we're gonna make use of graph theory. Okay, why graph theory? Why graph? Because we have a lot of variables. Okay, and that's why we call them, and these variables interact. Some are independent, some are conditionally independent, some are not independent. Okay, so we basically, because we're going to use the idea of, the independence and conditional, what is it called, the marginal probability and the like that we've done before. Then we're going to make use of probability theory. So the combination of these two, okay, is what we basically call probabilistic graphical model. Okay, so what I'm just to tell you now, the probabilistic graphical model is, using a framework to represent, large collection of variables, large collection of variables. So how can we actually model large collection of variables that interact? Okay, that's basically what we want to do. Now, of course, we're going to have, like I said, representation. It's like we're trying to using a graphical model to depict reality. Then the inference, we basically, the inference in statistics, like making judgments. Okay, we want to be able to take a conclusion based on what we see. Then learning, okay, so we're actually going to learn something from the structure. Okay, then decision theory, of course, we'll be able to, that was why I said what happens when it is a time to convert beliefs into action. We're basically going to use the idea of Bayes theorem here too. Okay, don't forget, well, the idea behind the Bayes is just like, okay, I actually have a prior knowledge of something, and when I collect data, okay, how has my previous or my prior knowledge change? Okay, we always have a way to update. Then we go into applications. Now, This is the definition of probabilistic graphical model. We actually want to capture, we want to represent a complex situation, and we want to use probability distributions on this complex structure. Okay, so that we'll be able to capture, because it is not all the time that we have independence. We can also have some form of independence that are conditional, which I'm going to review today. Okay, between the interacting variables. Okay, so let me just tell you this. Why do I need to use the knowledge of graph theory and probability theory to model complex situation? Because it is complex, it's going to be high dimensional, and how can we actually model high dimensional situation in a more compact way? I'm going to say that again. This particular approach, actually will enable us to model high dimensional complex situation in a more compact way. Okay, and let me tell you this. Let me tell you what we always want to do. We actually want to take a decision. Okay, we want to make an inference on something that you did not observe based on what you observed. I'm going to say that again. Maybe I go into my grandpa's house and I saw a picture, and that very picture is noisy. Okay, that picture is noisy. Okay, maybe I can't really see, the picture is not clear, and you now want to predict how the picture is going to look like. So it's like you actually want, given the evidence, you now want to figure out the probability of unobserved. Okay, how do I get the probability of unobserved given observed? That is what the PGM does. Now we got two types of PGM. We have the directed, one that we call Bayesian network, and we have the undirected one. But as far as this course is concerned, we're basically going to focus on the Bayesian network. Okay, now let's get started. Now, this is the situation. When I have two variables, when x1 and x2 are independent, based on what you have learned, okay? When x1 and x2 are independent, what is going to happen? The probability of the joint is basically going to be this. Any question? Any question? When x1 and x2 are independent, this is what you have. Then what if they are not independent? Okay, the joint is basically going to be x1, then x2 given x1. This is not a complex situation. These are just two variables. But what if in a situation where I have from x1 to xn, so many variables? Okay, now, and I want to find the probability of the full joint distribution, the probability associated with this multivariate. And there's some form of, dependency. Of course, I'm actually going to use without the graph, without using the graphical structure, that would be too complex. Now, using the idea of the graphical structure now, okay, we're basically going to write, look at that this guy, we're talking about product sign, right? It's trying to say xi, giving parent of xi, which means we're going to have some variables that depend on some another variables. And in this graphical structure, if a variable depends on another variable, the one that depends is going to call a child. Okay? And a child will depend on what? On parents, right? Right? A child depends on parent, right? That's why you see the probability of xi given the parents of xi. Now, for you to really understand. Oh, go ahead. Yeah, the probability of the joint of all the variables. The probability of the joint, just like the probability of the joint occurrence of all the variables. Now, I need you to pay attention now to what I'm displaying. Take a look at this. What do you see? Two events A and B are starting. They didn't depend on anything. Look at that. Is A and B is depending on anything? But what is depending on them? C. Any question? Look at that. C depending on AB. If I want to write the probability of joint based on this structure, now this is what I'm going to tell you. This is a graphical structure, right? When I put a probability on each of the node, it becomes a probabilistic graphical model. The way it is now, just a graph structure. No any number. Do you see any figures? It's just A, B, C. But if I indicate, so which means the probability graphical model is going to tell us we are putting into consideration the probabilistic relationship among variables. Now, take a look. If you take a look at what I have now, based on this structure, if I want to find the probability of the joint A, B, C, you know what I'm going to do? A and B, they are starting on their own. A and B, they don't depend on anything. That will be marginal. I'm going to write probability of A, probability of B, right? They are starting on their own. What about C now? I'm going to write the probability of C given A, B. Any question? Based on that structure, this is the probability of the joint. Is there anyone who have a trouble time understanding how from the structure, from the graphical structure, how you can write the probability of the joint of the ABC? The AB here are the ancestors. Okay, we can call them ancestors, like or the parents. C here is the child. And you know, we have some event that depend on another event or depend on two or more events. Now, because of that, there's something that we call directed edges. You know, all those arrow, okay? That's what we mean by that. Now, absence of an edge. There's an absence of an edge between A and B. Is there a connection between A and B? No. That's what we call absence of an edge. Now, and let me tell you this. We may say A and B are independent, but there's going to be a condition. A and B are independent, given what? Given C. That is what we call conditional independence. For instance, if I only have this guy, this is absolute independence. There's no connection between them. But the moment I have this guy, right, then A and B will be conditionally independent. So in probabilistic graphical model, we use the idea of conditional independence. Take a look at this. This is an example of absolute independence, which is the independence that we normally talk about, right? The probability of A, B, C, the joint occurrence of A, B, and C is just going to be the product of the marginal. Any question? This is an absolute independence. And we normally assume this a lot in statistics. But let me tell you, we realize that it may not be absolute independence. It may be conditional. Maybe that's why we don't get things right at times. Okay, now take a look at this guy. I want to write the probability of A, B, C. Okay, if I want to write the probability of A, B, C, A is the only event that is not depending on anything. Look at that, A. That's why you see the probability A. Do you see the probability A? But take a look at B. B is depending on A. And C is depending on A and B. Any question? Is there anyone who have a trouble time? How I actually write out the joint probability ABC from the structure. which means you may be given probability structure, a graphical structure, and they ask you to write the probability of the join. Any question? You're good, right? With that. Okay. We can have a more complex structure. Oh my God. This is a more complex structure. How many variables? Each node represents variable. How many variables do we have? We got 7 variables. Okay. This is a complex structure. You know, we have situation where variables are interacting, right? Now, what are the ones that started that didn't depend? The variable that did not depend on any is x1, x2, and x3. Oh, sorry. Yeah, x1, x2, and x3, they are starting on their own. Do you see that? Do you see x1, x2, x3? They did not depend on any. They don't have ancestor. They don't have parents. And if they don't have parents, we're going to write them marginally. It's going to be probability of x1 multiplied by probability of x2 multiplied by probability of x3. That is what you are saying there. Now, let's take a look at S4. Oh, S4 has 3 parents. Did you see that? X4 has 3 parents. That's going to be probability of x4 given x1, x2, and x3. That's what you see there. What about S5? Oh, S5 has 2 parents. Do you see the direction of the arrow, right? What about, any question? I'm done. Even if you have more complex structure, you can easily write out the probability of the join. Any question? Okay. Now, you know, the general factorization, like if I want to write all that in a short form, I can just write that in a short form. Now, there's something I wanted to see. I want to talk about the issue of when A and B are independent conditionally. Okay. Now, you know what I'm trying to say here. A and B are independent. You know, always refer to this guy, refer to that sign. Independent. A and B are independent. Giving what? Giving C. But let me show you the structure now. Take a look at this structure. Okay. Now, if I can say A and B are independent, okay. Now, if C is not observed, okay, if C, let's say C is not observed, then we're going to say A and B are not, you know, let me first show you this so that you'll be able to understand what I mean. Let me start from here. Now here, C is observed. That's why it is shaded. Then you know what I'm trying to tell the world. A and B are independent, given that we have observed C. But take a look at this. A and B are not independent. Look at that sign. Oh, it means not. A and B are not independent, given that we haven't observed C. That is nothing. Do you see that? Now, take a look at this. If I now have this guy now, where A and B are independent given C, do you know that if I want to find the probability, okay, I'm going to show you something now. Based on the structure, what is the probability of A, B, C? Based on the structure is the probability of A, B, C is basically going to be the probability of A given C, then the probability of B given C. Do you see that? Based on the structure. You see that, right? So the probability of A, B, C and multiplied by probability of C. You know why probability of C? Don't forget C it doesn't depend on anything. You see that, right? Now, if you take it, well, let me write that so that you'll be able to understand. What I mean is, if I want to find the probability of A, B, C based on the structure, I'll first write probability of C, then the probability of A given C, the probability of B given C. Okay, take a look at that. Now, this guy here, do you know I can combine them to be what? The probability of AB given C. Look at that. A comma B given C. Okay, this is probability of C. This is probability of A, B, C. So if I want to find this, I can do the probability of A, B given C equal probability of A, B, C divided by probability of C. That's what you see. Any question? Any question? Like I said, do not hide your feelings. Ask question. If you don't really understand, I'm going to explain. Okay, it means you are good. Now take a look at this. What if you say something like this? And I want to get the probability of ABC. Okay, the probability of ABC is going to be probability of A. A does not depend on anything. I needed to pay attention to the arrow, right? This is the arrow. Pay attention to the arrow, right? So it's going to be probability of A, but C depend on A, and B depend on C. Look at that. Now, if I want to make inference, it may not be all the time that I want to get probability of ABC. What if I want to get probability of AB from ABC? What am I going to do? What I'm actually going to do, I'm actually going to sum all of that over what? Over C. This is what I'm saying. Take a look at this guy now. Take a look at this guy. I have probability of A, B, C, and I'm interested in probability of AB. It means I'm not interested in C. If I'm not interested in C, you know what I'm going to do? I'm going to sum everything over the range of C. Does that make sense? When I sum that over the range of C, then the whole of this will become probability of B given A. The C will go away. It means I'm marginalizing that. Any question? And if you take a look at what I have here, A and B are not independent, giving nothing. Now, when I say A and B are not independent, what are we trying to say? They depends, giving nothing. Take a look at that. Now, I want you to take a look at this. When we don't observe C here, what if in a situation where Z is observed? When C is observed, like we're shading C now, the probability of AB given C equal to the probability of ABC divided by that, right? And the probability of ABC, you can get that from the structure, right? Probability of A is starting, the probability of C given A, probability of B given C, right? Now, there's something I want you to see now so that you'll be able to understand this. Now, see, I said the probability of AB given C. Of course, AB given C is going to be all of that, joint, all of that, right? Divided by the probability of C, isn't it? From the law of divided by probability of C. Now, you can get this guy from the structure. What is the probability of joint based on the structure, based on the graph? That's going to be probability of A, right? Then the probability of C given A, then the probability of B given C, all divided by probability of C. Now, do you understand how we get that? Right? Now, if that is taken, take a look at this. Oh, do you know that this guy, if I write probability of A, probability of C given A divided by probability of C, this will be equal to what? Can somebody tell me if this is probability of C If I want to rewrite that, what is going to happen? A, can somebody tell me? If I want to go by, when you take a look at this is like A intersection C, right? If I now, and what about C intersection A? Okay, so C intersection A, right? Take a look at A intersection C. You're basically going to see that that is going to give you, that the probability of is going to give you this C giving A. Now let us see. If you cross multiply, this is the same thing as that. Let me see. A, C giving A. Oh, sorry. I wanted to say A giving C. Sorry. A giving C. Do you understand now? Thank you for that. So this and this. So because of that, I can say the whole of this to be this guy. That is what I plug in here. You see that? I've already. So take note of that. Now, the next thing I'm going to show you now is this guy here. The probability of A, B, C. Okay, when you look at the joint structure, A, okay, A and B starting separately. A and B are like parents. Probability of A, probability of B. Then C giving A, B. The probability A and B are independent if you have a product, right? Probability of A times probability of B. And here we're trying to say A and B are independent, given nothing is observed. The same thing here. Now, for you now to really understand this in terms of application, so that it doesn't look as if we're just doing maths, though we're doing maths. So let us now do maths that makes sense. Take a look at this. Practical example now. I wake up in the morning, okay? And I open my door and my grass is wet. Okay? If my grass is wet, there are two things that will come to my mind. What are the two things? It's either the sprinkler is on or rain. Does that make sense? And if rain is falling, do I need sprinkler? No. So whether I'm actually going to put on a sprinkler or not, it depends on the season. Now take a look at that now. So which means for grass to wet, it depends on whether rain fall or sprinkler is on. And don't forget, using sprinkler depend on rain. Any question on that structure? Any question? Okay. Oh, go ahead. Oh, can you say that again? Now you got it now. What I'm trying to say that we don't use sprinkler when there's rain. And that is why using sprinkler also depend on whether there's rain or not. But rain does not depend on anything. Now, if I want to write, now I'm going to use sprinkler is going to be S. Okay. Grass wet is going to be G. Rain is going to be R. Based on the structure now, if I want to write the probability of the joint, the probability of XRG, what am I going to start with? I'm going to start with the marginal, the one that doesn't depend on anything. So probability of R, the probability of S giving R, then the probability of G giving SR. Any question? Any question on that? That's practical application. Okay. Now, do you know on this I can make inference? When I say inference, I may decide to say, I want to find the probability that my grass is wet. The probability of G. Oh, if it means I'm interested in only grass. If I'm interested in grass, what am I going to do? I'm going to sum out the other variables. What are the other variables? Rain and sprinkler. That's why you see two summation. I'm actually going to sum out the one I'm not interested in. I'm only interested in grass. And what if I'm interested in probability of my grass is wet giving rain? This guy here, the probability of my grass is wet giving rain. Then I'm actually, and don't forget, you know, two things actually depends on rain. Let's go to the structure. What are the two things that depends on rain? The grass wet depends on rain. Sprinkler also depends on rain. So if I'm now interested in the probability of grass wet giving rain, then what am I going to sum? It means I'm actually going to sum sprinkler out. So I'm going to use the probability of sprinkler and grass wet giving rain. And that will lead to the other guy. Now let me take you to a more complex situation. COVID. Take a look at that. A lot of things was done for them to be able to determine what causes COVID-19. This is a more complex structure. Look at that. The COVID-19 depends on the coronavirus HKURI, the platelet, and when somebody have COVID-19, it's either the person go to regular ward or to the other. You see, this is a network. It's a graphical network. So to tell you the probabilistic graphical model as application in medicine, a clinical trial, something like that. Look at that. We can make a difference here too. Now, what about a medical diagnosis of lung disease? Look at that. Now, this is an example of probabilistic graphical model now. On each node, you can see probability associated. Now, let me tell you smokes. In the data that is available, 20% smoke of the patients smoke. 80% do not smoke. When you see T means true, F means false. Those are probability associated with each node. We call all this one conditional probability. Now look at what determines lung disease. Smoke determine, at times, let me tell you this. I'm going to tell you why we're in a complex situation. When you hear this, when you hear that, a lot of things will come to mind. We can have a symptom that could lead to any more than one disease. Somebody who have a COVID cough, somebody who have fever also cough. Look at that. Now take a look at this. Lung disease. Okay, smokes. We believe that smoke actually causes lung disease, and the lung disease. What are those symptoms that you're actually going to see? Oh, shortness of breath, chest pain. Okay, and look at that again. Lung disease also cause cough. Cold also cause cough. As an example. What about in supply chain? Look at that. Even in supply chain, okay. There was an earthquake in the northeast of Japan that actually destroyed supplies. Take a look at that. You have supply 1, supply 2, supply 3. Okay. Now, when tornado, you can see the global destruction, economic collapse. Okay, actually depends on what. Look at that, supply 3. Okay, can you see that? And when there is an earthquake, look at that. Look at tsunami. Tsunami affects supplier 2. Look at that. Look at supplier 1. Labor strike. There's something that I call local disruption, and global destruction. There are some events that will lead to local disruption. There's some event that will lead to global. Okay, the one that lead to local now, like a labor strike, like issue of flood, fire. Okay, take a look at that. And if supplier 1, supplier 3, they are affected. The global disruption. Look at that. This is an example. Okay, I'm gonna go into criminal justice now. Take a look at this. I'm in criminal justice now. What do we call recidivate? Recidivate is the probability that a criminal will reoffend. You know, in the court of law, when the court has already established that the accused is guilty, they don't just sentence immediately. They actually go to consider some factors. They call it aggravating factors. And they're going to see maybe they should increase sentencing or decrease sentencing. And you know what they're going to do? They will need to put into consideration what is the ability that this guy will not reoffend again. What is the ability that this guy will not commit offense again? And what determines that? The priors, history of offense. Okay. Then that also depends on the type of crime.